We've been talking about making decisions in the face of uncertainty. And so we've looked at what we call the state of nature. That essentially is our unknown parameter, theta, which typically is tied together with the data that we may be able to sample from. Those are the x's, quote unquote. And then the decision or the action is going to be essentially our estimate of theta. And each one of these come from a space, and those spaces usually coincide since the action essentially is to estimate theta. Typically we use a fancy uppercase A for the action space, and we use an uppercase theta for the parameter space. Okay, so now we want to bring in the consequence. The idea of the consequence or loss, as we'll refer to it. So, given our estimate, our action, and also the true state of nature, then it's obvious that there's going to be some sort of consequence, whether it's good or bad. And so again, we're going to look at that in terms of loss, and that's going to be a function of. So loss is a function of theta and the action we take. So let's look at that. So the loss function is technically a mapping from the Cartesian product of the parameter space with the action space, not into the whole real line. For technical reasons, we require that it gives us a value that is bounded below. So that's why we have that negative k there, closed interval negative k comma infinity. And here k is just some positive real number. And so then for a given state of nature, for a given theta, and an associated action, little a, the value L of theta comma a measures the loss associated with that particular decision. All right, so let's look at an example. Let's continue an example that we looked at earlier, which dealt with a drug company that is considering putting out a new drug. And we had the parameter theta, which at that time was a vector. Let's do it this way. And theta 1, theta 2. And I think theta 1 essentially was the efficacy of the drug. So that would be, I think it was the proportion of the target market for which the drug would be effective or something like that. And then theta 2 is what we want to focus on here. Theta 2 is the proportion of the market that will be captured by the new drug. So essentially that's the demand. And I think that's what the book refers to it as. So since theta 2 is a proportion, the parameter space and the action space both will be the closed interval from 0 to 1. And as you see there, often those two are the same. And so now we want to look at the loss. So our loss function here, we look at two different parts. So in the first case, if little a is less than or equal to theta 2, so if we underestimate the proportion of the market, or if we underestimate the demand, then we're going to say the loss is theta 2 minus a. And you can see that that would be a non-negative value. So since we're talking in terms of loss, positive is bad and negative would be good, because a negative loss would be a gain of some sort. Okay, so then the other case would be, well, what if we overestimate the demand for this new drug? You can see there that in this case, the difference between those two, the value a minus theta 2, has been multiplied by 2. So it seems, this is straight from the textbook, So in this case, an overestimate is being weighted sort of as twice as bad as an underestimate. And so that's one example of a loss function. And we'll do a lot with loss functions as the semester progresses. At this point, we're going to sort of take a sneak peek into Bayesian statistics, and we're still going to continue in the context of this example. And remember, what we want to do is estimate theta 2, this unknown proportion, this demand for the drug. And so a reasonable experiment would be what you see here, and that is to randomly sample little n members from the target market, and then let x be the random variable which records how many of those say that they would buy this drug. And so reasonably, we could say that that random variable x is binomial little n comma theta 2. And remember that the PMF of a binomial random variable is what you see here, the binomial distribution. Usually, instead of theta, we see little p. That's just a typical letter used there, and that should be f of x given theta 2. And so that is one way, that's sort of the classic way to investigate or estimate this unknown proportion, this demand parameter. So we're going to also think about, well, how could we use our prior knowledge, or how could this drug company use their prior knowledge to gain more information about the value of theta 2? And so let's suppose that historically this company's drugs of a similar type have captured between 1/10 and 2/10 of the market. So a simple yet valid way to model this would be what you see here. Let's model theta 2 as a uniform value between 0.1 and 0.2. And so you can see here that even though we don't know what theta 2 is, but we have some idea about theta 2 based on prior information, and so we manifest that prior knowledge in terms of this prior distribution. And you may have been wondering, why do we call this the prior distribution? And with this preview of Bayesian statistics, we're going to see why this is called the prior distribution. Okay, so if we go with theta 2 being a uniform distribution, then that leads us to what you see here. Remember that since this is a valid distribution, we've got to be able to integrate under the curve, and essentially the curve is on that interval from 0.1 to 0.2. It's just a horizontal line. We just have to figure out how tall does it need to be, and of course in order to ensure that the area under the curve, essentially the area of that rectangle, is 1, then it's got to be a height of 10. So that you have the base is 0.1, the height is 10, so the total area is 1. And that's just comes straight from the uniform distribution. And so there we have a prior distribution for theta 2. So now what we want to do is we want to combine all this information together. So what we would like to do is take our prior distribution together with the distribution of the data based on our sample that we referred to earlier, and we want to be able to put those two together and get an updated understanding of the distribution of theta. And so now hopefully it's clear why we use the word prior, right? Why we use the word prior back here, because once we have that, and then when we combine it together with the data, we have what's called the posterior distribution of theta. So that's the distribution of theta given x, given our data. So it's like It's our updated understanding of the parameter once we have access to the data, to some sort of data. Okay, so we'll do more with that specifically as time progresses, but this is just an idea of Bayesian statistics, and this example seems to be a good context in which to give that preview. Okay, so let's look at another example and get back to this idea of loss. And so in the cases where our parameter space and our action space are both finite, then the loss function is essentially a loss matrix. It's basically a table. So in the textbook, there's an example of an investor having two options. So the first option is to buy risky bonds. And so the initial investment is $1,000 if they buy the bonds. Okay, if they buy these risky bonds, the initial investment is $1,000. If those bonds mature, then the person will gain $500. They'll get back their original investment of $1,000 plus an extra $500. If, however, the bonds default, the investor has lost $1,000. Now we need some information about these risky bonds. We sort of need some prior information, if you will. And so let's assume that these bonds will default with probability 0.1. So in other words, there's a 10% chance that the bonds will default and a 90% chance that they will mature and the person will get back their initial investment plus the extra 500. Okay, so that's one option. Let's also suppose that there's a second option available to this investor, and that is some really, really safe investment which will guarantee a gain of $300. And this is in any context, this is like separate from the bonds. And so whether the bonds default or not, this investor would still get $300 if they go with the safe investment. So now here's the investor's setup, and he or she needs to make a decision. And in this context, loss is just going to be simply any monetary loss. All right, so then let's consider our parameter space, which is here. So let's say theta 1 would be the occurrence that the risky bonds do not default. And then theta 2 is that they do default. And then we've got to make a decision. And the decision is, do we buy these risky bonds or go with a safe investment? And so you can see there, little a1 is where we buy the bonds. Little a2 is safe investment. So we have two possibilities for theta and two possibilities for a. So let's see what's the setup. So let's first look at the loss matrix. And remember that we're talking in terms of loss. So bigger is worse and smaller is better. So if you're just kind of looking at this loss matrix, which our objective really here is to put this together, but since we've already got it there, you can see that the best situation occurs here, where the loss is negative 500. So a negative loss is a gain, right? So that'd be a gain of 500. And that would be the case where the person opted to buy the bonds and they did not default. Okay. So just to make sure we understand this matrix, let's consider first the safe column. In the safe column, if the person decided to go with the safe investment, then it doesn't matter whether the risky bonds default or not. They're still going to gain $300. And so the loss is negative 300 in both of those cases. And then, so hopefully you can sort of see the validity of that loss matrix now, because the only other option we need to consider is this option here. And this would be the case where the investor purchased the risky bonds and they defaulted. And so in that case, the person really would suffer a loss, and that loss would be $1,000. So that's the loss matrix. So before we go to Part B is going to ask us about the prior information. So just take a second and think about, what is the prior distribution for theta here? because we basically have been given that in the context of this problem. Okay, and so the key is right here, right? We were told, we assumed, rather, that the bonds default with a probability of 0.1, and they will mature then, with, of course, with a probability of 0.9, and that's the prior distribution. And that's what we have here. And you can see there a couple of ways to write this. Probably the more standard way is this first way. And so the PMF, this is what this would be. This is a probability mass function, because we're talking about a random variable, theta here, with only two possibilities, default or no default. And depending on the value of theta, we'll have different probabilities. I just want to mention, though, an alternate notation for that is what we see here. And so theta can be, if theta is equal to theta 1, then that will be with probability 0.9, and theta is equal to theta 2 with probability 0.1. So both of those convey the same information, even though the second one doesn't refer to pi explicitly.